So before we begin to listen to all of our distinguished speakers today, I'd like to welcome to all our distinguished guests, participants, ladies and gentlemen. Thank you for being part of this panel, and this is very crucial on this topic of climate change in the tropics, as we are all indirectly or directly are experiencing the impacts of climate change. So for those who are going through the challenges, let us all make our small prayers and dua. May Allah SWT grant them peace in whatever situation that they will be. So we know that the impacts of climate change in the tropics is becoming very critical, as we are the communities in the tropics being the frontliners of these impacts of climate change. And being the frontliners, we have to address this situation in an urgent manner. And so how could we bring our collective effort together in addressing this critical moment? Just for a very brief introduction, we realize that the recent Intergovernmental Panel on Climate Change report from the Working Group 1 confirmed that humans are the primary cause of climate change, and that is now the global temperature over the past decade was about 1.1 degrees warmer than it was in the 1850 to the 1900, and each of the past four decades has been the warmest. So that's why we are here trying to address together this issue, especially on the increasing urgency that we have to look at building the climate resilient development for us in the tropics. So we have here all our distinguished speakers, Professor Dr. Edwin Aldrin, Professor Ulo Mander, as well as Associate Professor Dr. Liu Juning. Let me kindly read their very well specialized background today before they begin to share with us their vast knowledge on this topic that we have. Professor Dr. Edwin Aldrin is a prominent Indonesian researcher and meteorology expert. He has held key positions, including being the head of Climate Change and Air Quality Center at Badan Meteorologi, Climatology and Geofisika, and head of research and development. Currently, he is now the research professor at the Agency for the Assessment and Application of Technology and won the Habibie Award in 2018. From 1993 to 2009, Professor Aldrin was involved in artificial rain technology, and he has led climate initiative from 2009 to 2016, and he served as the vice chairperson of the IPCC Working Group 1 from 2015 to 2023. And recently, in 2023, he was again re-elected for a second term, continuing his impactful work in climate science. So welcome, Dr. Edwin. We also have with us today our distinguished Professor Ulo Mander, Professor of Physical Geography and Landscape Ecology, University of Tartu, Estonia. And Professor Mander's research interest is on the biogeosciences, carbon and nutrient cycling in wetland and forest, landscape ecology, and ecological engineering and riparian buffer zone. He was a supervisor for many of these PhD students, CCs, and he's also still very actively supervising his PhD students as well as postdoctoral researchers. And he has participated in 20 European Union 5th, 6th, and 7th program, Horizon 2020 and Horizon Europe project. Professor Ulo Mander was a visiting professor at the research center in Germany, Sweden, Norway, Japan, China, USA, and France. And he is also a member of the advisory board for 7 scientific journals. And additionally, he now has participated in expedition to tropical peatland forests in Peru, Malaysia, Reunion, the Republic of the Congo, and Uganda. Welcome, Professor Ulo Mander. And now we have with us also our Associate Professor Dr. Liu Juning. who is from the Department of Earth Sciences and Environment, University Kebangsaan Malaysia. Dr. Liu Juning is a distinguished climate scientist specializing in tropical meteorology and regional climate dynamics over Southeast Asia. His research focused on the inter-annual and long-term climate change timescales, and he is active participant in the regional research collaboration and also served as the council member of the World Climate Research Program Coordinated Regional Climate Downscaling Experiment, Southeast Asia Domain, or in short, CORDEX, SEA. So together with his colleagues from Southeast Asia and other international agencies, they now run this regional climate model to provide high-resolution future climate projection for Southeast Asia region, benefiting the regional users and contributing to the IPCC assessment. So welcome, Associate Professor Dr. Liu Juning. Okay. As time is really not so much on our side, let us begin with our first panelist today, Professor Dr. Edwin Adrian, with his presentation.
Thank you, Professor Sharina. Let me study about this year. So I want to bring this topic, sustainable hormone and climate change in Malaysia. This is very interesting, and then I bring this topic recently to hormone seminar in Mumbai. I think few months back. I think in Mumbai. Okay. I bring this figure as the first one in Kalimantan. I think this is peatland and forest in central Kalimantan. This is the experiment we make in this island, and then you can see that the site there, over here, and then looking at the data, we have this number, and then we have the mean of the 300 GPP, RE and NE blocking the drainage for in the year 2002. This is year 2002. This is very normal year, and then this is done by Japanese and Indonesian scientists for the emission sink and the source of emission forest fire. And this we have the number 300 centimeter meter square per year, and then it is the 1/3 of the absorption of zinc from the metal of forest. This is the forest in Kalimantan, and then we need. So actually, what we learn from here that is, whenever we have fertile forest, that we can use to replace the carbon sink by the emission reduction from forest from 400 and 200 gram per carbon per meter square per year. This is the largest source of absorption carbon pool in Indonesia. And then we put that the acquisition of the last emission of this organic with the fact of the large capacity of absorption of the virgin forest. And then we have this number. We only need only 1/3 of the area missing. So 1/3 of area missing is can replace the virgin forest in Kalimantan. So they can release missing, and then including the stopping the processing in Kalimantan. So this is the number we have. The palm oil carbon uptake brought by this island. So palm oil export in the world, which is Indonesia becomes a competitor for Malaysia, because the two together we almost produce 90% of the whole world export of the palm oil. So this number is very big, and then this is what we have Indonesia and Malaysia, and together we can supply the whole world. Is 90%, 92% of the whole world. So according to the IPCC, the export of Malaysia and Indonesia cover 92% of the need of the export of palm oil in the world. So this is very large number, and then can supplied by the Kalimantan and Papua alone. So this one. What is IPCC say about the oil emission? So according to the old IPCC report, this is year 1 emission. The factor is 40 ton CO2 per hectare per year. So and then higher for the drainage after drainage. So IPCC also use the report of the POC for one year, and then so on like that. So this is the risk of oil palm plantation due to forest fire in Kalimantan Island. This is if you see the number of this, and then you look at the expansion of the many of the net CO2 emission for the palm oil in the year 2010-2020, we have this number. And then when we have the number compared to the El Nino years, this is during El Nino years, 2006 to 2007, compared to the 2017-2018. So the number is very big for the El Nino years, because we have also the forest fire during the El Nino episode. So this number, this figure show you the fluctuation of the carbon forest fire in the year 2006 and then year 2015 and 17. And then after that, Indonesian palm oil production is going to be affected by the El Nino years. And then if you're talking about palm oil suitability, this is the suitability of the topics of the palm oil. So mostly we are located in the Indonesia, Malaysia, and this is the Congo Basin and Brazilian area there. And then we have in the modeling, if you do modeling like this, you can see when we have a new modeling. This is from the model. We say we have the temperature, and then so like this. We can vary the temperature and humidity and so on, and then we can apply the future climate of the what will be the future climate of the suitability line. And then we have this one present day oil suitability, and compared to the 2050 and then 2100. And here we have that we have until year 2100. Still we have very suitable very suitable land for palm oil. So this is even 2010 is very suitable for palm oil. And then when we have another modeling study for the present day palm oil suitability, this is for area of the Southeast Asia area 2070 and 2030, and then even year 2100, it is very suitable for area for palm oil. And then this compared to the suitability of the palm oil during the future year. And this is the scenario for future year. This is a scenario from IPCC. This is by this one area suitable for palm oil, and then we still have very suitable for the palm oil suitability. Okay, and then the consensus of global impact on the agricultural production. This is global warming and then higher physical region and so on like that. Consensus this is food security to be affected, and then considerable resistance to the climate change via adaptation of the climate change. And then like this one. So example, this is the story of the forest fire in 2015 and so on like this. This is month July or until November. July and November. And then we compare to the different measurement of the according to some other paper how they can measure. So and then conclusion that for clearing online of the virgin forest in Indonesia, we need 1/3 of the forest plantation and virgin forest to balance the emitting carbon in the virgin forest. And then the Martin coordinate is very suitable for area for palm oil. So we can see the year 2017, year 2100 even still very suitable for palm oil production. Future climate model using asset model indicate the reduction of suitable land for palm oil in Indonesia, and still very suitable for year 2100. The need to effect climate modeling using soil type, new APC model for the CP and the SFP, as well as ecological dynamic. So this is the basic area of the model after model. Okay, I think that is what I want to say. The palm oil still very much in our. Thank you very much.
Thank you, Prof. Edwin. Yes. So this is a very important point that you have highlighted first regarding the carbon dioxide emission due to oil palm plantation and its impact on the climate change. So now we will move to Professor Udo Manda, who will also be sharing with us on his presentation in relation to the greenhouse gas emission in the tropical peatland forest. Well,
thank you very much, Sharina. And tropical peatlands, what we know, that this is, the tropical peatlands are quite well studied in terms of distribution in the earth. All the peatlands cover only 3% of terrestrial earth, but containing up to 30% of organic carbon, as well as up to 10% of nitrogen. And when we are losing them, global warming is not easy to stop. The tropical peatlands cover about 14% of all the peatlands, but they contain 60% of carbon. And most tropical peatlands are peats from forests, and they are CO2, carbon dioxide, methane, and N2O, or nitrous oxide emissions, vary with wet and dry seasons. But however, due to the global warming, this pattern has been really changed, and it's very hard to predict when the wet season coming and how long it is. There might be many droughts and many floodings, and tropical peatlands are really global hotspots of methane and also N2O. We know that. But what we don't know, and I'm explaining at the end or during the presentational slides, that all the estimations of methane and N2O fluxes are made on soil measurements. We don't know what is doing the canopy. There are evidences from our equarium systems in the temperate zone in older forests that N2O is somehow absorbed in the canopy. What is the mechanism? Maybe physical, maybe microbial, maybe anaerobic sites, tiny or microbial one in leaves, because N2O to be reduced need obligatorily anaerobic conditions, the NOSTED gene. Well, and also no models are considering some important factors, but we have also got with our studies that in contrast to CO2 or CH4, this N2O has kind of unimolar or hyperbolic relationship to soil water content, meaning if it's very dry, that's not enough water for the microbes, and the release of N2O is slow. And in opposite, if it's inundated, very wet, the process of denitrification is coming to the end, and we get the result of N2, which is harmless, but we all breathe every day. So, and also no microbial aspects are included, especially ratios between the producers and consumers in both processes, nitrification and denitrification, as well as integrated analysis of isotopologues, the 15N and its location in the molecule. The atoms are really good indicators to distinguish between the processes and so on and so forth. And still, restoration is a big hope. And I guess that in tropical peatlands, which partly should be restored, the chance for restoration are better because of very recalcitrant carbon. And if to do that in proper way, the chance is good. So, only one more. Could you? Yes. Well, we know that, okay, CO2 is easy to analyze regarding the trees. It's photosynthetically used and releases also some CO2 from the stems, from the leaves. It's aerobic respiration. But the trick is we really don't know what is the role of CH4 and then N2O from the tree stems releasing and also in the canopy. Well, both consumption and release can be seen in this process. And the interesting thing is that also the leaves are releasing a lot of methane. They can absorb but also release. And this is a physical process, most probably. One found in Germany by Kepler already many years ago, but a little bit problematic was they calculated the global release of methane based on laboratory data. Next one, please. Yeah, and we're running now 2 EU projects. It's Life 4, quite ambitious. That's why we are here now in Malaysia. We follow with expeditions by Tropi people from Alvadam and also with Tong and Cebu. Second and third are the wet bed rotations. And we have been doing, another one is just related only to N2O, to get more information about this maybe less studied component of greenhouse gases. And we have been working, and still working, Quistococha in Peru, Pena in Congo, Marudam at Betong, and we have potentially contacts with many peat and study centers around the world, and we would be very happy if more people from Malaysia could be also included. Yeah, and what to say, low soil emissions in tropical peatlands are significantly higher than in other areas. And N2O is the main actor among the three greenhouse gases. As interesting as it is really to say, because of very high radiative potential. It's 300 times more than CO2, and also the life time is up to 100 to 120 years. Next slide, please. Yeah, and this is both Limepore and also the peatland N2O setup. We measure components from the soil, from the stems, above the canopy, which is more exciting, using different modern methods, including isotope analysis, microbiome analysis, and also eddy polarians with 10 Hertz frequency for all the gases. N2O is still problematic. We are establishing the N2O system really soon. And the next one, please. Yeah, and restoration, very complex picture, but we know that what's happening, what are the natural systems, tropical, which is put here, open bogs and fens and forested areas with relatively low emission, even in terms of the methane, only from the open pools. The fluxes are more, and when it's disturbed, so to say, then we get much more intensive fluxes. And how to restore, which is very important task for all the European countries, creating a lot of discussions, especially because of afforestation. And there is, to my mind, one chance, a better chance for tropical countries. The peatland forest in here is formed from trees, lot of lignine, and also phenolic compounds, aromatic compounds, whereas they're easily decayable. The cores have been released, but the most of the peat mass is still recalcitrant. And culture, of course. In the north, there are different crops like white berries or energy crops, reed and miscanthus, which is a very high, somebody called a giant reed, and also other species. But in tropics, the good chance are with different plants, like salm, which likes to grow in wet conditions. So it's not completely hopeless. If we really can do something together and more properly. Thank you very much for your attention.
Thank you, Prof. Olumanda, for that note, and especially for the hope that we are all.
So I need to sit here, I need to stand here. Yeah, it's okay. Good afternoon, ladies and gentlemen. So what I'm going to do is, for the next 5-6 minutes or so, I'm going to reiterate how complex the weather system is in the tropical regions, especially in the tropical maritime continents where we are at currently. Okay, so it's very complex, basically, the weather systems and circulations over these regions. So if you do your measurements in the ground, you always find that your measurements tend to have a seasonal variations, right? So the seasonal variations is largely dominated by monsoon. Right? So we have these two regions of monsoon that fluctuates oppositely within the year. And in addition to that, we also understand that every 3 to 7 years, the sea surface temperatures over the Central Pacific tends to warm up or cool down abnormally. So that gives us phenomena either El Nino or La Nina. And apart from the signals that come from the Pacific Ocean, so we also have every 3 to 7 years, the flipping of sea surface temperatures anomalies over the Indian Oceans, and that can anomaly modulate the precipitation, the temperatures of these regions. And on top of that, at a very shorter time scales of about 30 to 60 days, right? So we have also a phenomenon, what we call the mid-Julian oscillation. So this tends to modulate intra-seasonal variations. So if you do your measurements of temperatures, fluxes, at high frequencies, you probably see variations of about 30 to 60 days. I'm not sure, probably there, right? Because we know that these climatic systems massively influence us. So, and of course, when the world gradually warms up, the interactions is expected to alter. But I would like to reiterate here is that we really don't know much about that, right? Okay, so the tropical regions, whatever that happens in the tropics actually does not stay in the tropics. So it has the potential to actually propagate, the signals can actually propagate off tropics to the temperate regions through what we call as heavy circulations. So if you don't already know, over the tropics there are 3 regions which is convectively active, right? So one over the Amazons, and the other one over the Western Africa, and the strongest one is probably residing in the maritime continents. So whatever happens at the surface can alter the circulations, and these signals can actually propagate northward and southward through what we call the heavy sails. So if you do something here, so the signals can actually push towards the temperate regions, extratropics, and then that can feed back into the systems that influence the tropical regions. So the recent studies, not from our group, but from our colleagues in Taiwan, has shown that if you deforest the maritime continent, right, so that perturbation itself is strong enough to send signals across through the northeastern Pacific and influence the sea surface temperatures there. And that signals can actually chip into the tropics and influence various maritime continents. So that is the kind of signals that we're talking about. All right, so changes in the tropics. So over the years, we have quite a bit of data, so quite a lot has been learned. We know that at least the tropical cyclones in terms of frequency has changed, right? But put in mind that changes are not uniform across the tropics. So for instance, the frequency has changed over the Atlantic Oceans, but we know over the Western Pacific, the frequency is actually reducing. But overall, the strong one is increasing in frequency, so that's what we have learned, right? And also, we know the tropical region is actually expanding at a rate of about maybe, the rate is actually quite uncertain, but the rough estimation is probably about 1 degree every 25 years. So there's a rate of how fast the tropical expands. And then we know that the marine heat wave is increased in terms of its intensity and frequencies over the years, and we are expecting that to increase also in the futures. But of course, how fast it increases and how intense it increases depends on how the world evolves, right? And of course, the shift in rainfall patterns, and I would like to interact here. The pattern is not simple, so it shows very remarkable spatial temporal variations. Depends on season, depends on where you are talking about, and it's very complex. And also over the tropics, we know it's one of the regions. If you look at if you track the sea level rise from the satellite altimetry, so you get to see that the tropical Western Pacific is actually the regions where the sea level rising rate is the largest, is the fastest, right? And we expect that characteristics to continue into the futures. Right? So all these changes is expected to alter many climatic associated variables, chemistry variables, biological variables, etc. Which processes at this point of time, I believe, we don't know much. Right? right? So there are a lot of in situ measurement, yes, right? But how much we really understand how these measurement of flux is connected to the large scale convex, I believe it's largely unknown. Right? So yeah, this is just another picture to show how spatially and temporally the changes of the rainfall patterns can be into the futures. Right? So you can see here, you can see, for instance, let's look at the early centuries, right? So this is the changes projected by assuming that the emission is uncontrolled, right? So you get to see the wetting signals, right, over the mainland Indochinas. But if you look at the summer times, so you get to see some dry signals over the maritime continent. Right? So as time goes by, you can see that the signal is getting stronger, yes, but it does show some very complex patterns. So gaps and challenges. Of course, I look at it from two different perspectives: scientific and policy and practice. Yeah, so we have a lot of measurements, but really, how do we quantify and try to model, right? Try to set up models to use it, to try to understand how the connections between the tropics and much larger scale, right? So there are difficulties in putting all the components together, let them interact in the models. And then the model resolution is also one of the issues, because if you look at IPCC models, mostly global models, and then they're running at hundreds, 200 kilometers per grid, right? And the CNIPS, the Carbon Model Incorporation projects, does have an initiative called the Cortex, coordinate the downscale experiments, where they downscale the information to 25 kilometers, 10 kilometers. But that's still, from the perspective of national usage or local usage, is still very costly. So you really need much higher resolutions, but that comes with the drawbacks. With much higher resolutions, information that you get, the uncertainty is also increasing. Right? So that's the difficulties we are facing. And of course, we know tropics, if you cut across tropics, basically the areas where the data is scarce. So you have difficulties putting sensors. And what's the point? I think the largest challenge is really to communicate the scientific findings to the policy makers and the practitioners. So even if you able to do that, right? So to me, over the years I've been working with policy people, working with engineers. Not surprised. This information, these people are usually underinformed. Right? And then even if you manage to get the scientific knowledge across, still, bounce the problems. We have to make decisions under very large uncertainties. So how do you make sure that you make the correct decisions, no regret decisions, with such information which is very uncertain, right? And even if you are able to do that, there is still challenges by converting all this understanding into engineering practice. So you're talking about adaptation design, structures, buildings, and natural gas solutions. How do you make sure that your solutions is the one that best suited for the futures? So if you don't know the futures, how do you make sure that whatever you do is in the correct directions, right? And then there are a lot of social economic factors. So it seems that the government nowadays they are more focused on mitigations, right, decarbonizations, rather than adaptations. But in matter of fact that through discussions we do understand that the mitigation and adaptation usually need to, optimally they need to be done together. So you can't really separate them from each other and then address them separately. So those are the difficulties that, at least from my experience, that we understand. There's still a lot of challenges we need to overcome. Right?
Thank you so much, Dr. Julian. Yes, you have already with us to this very critical time where Dr. Sharina addressed the gaps and the challenges. So we have heard from all our distinguished panelists regarding the